begin just by quickly summarising where we've got to in Shor's algorithm. We started by saying we've got a large n that we'd like to factorise. We decided that if we could find a non-trivial square root of 1 mod n, then it would be done. And a good way of finding such a thing would be to take an x, work out its order mod n, get some r, and hope that r was an even number, and if not, then just try again with another x and keep going until you hit an even number. And that if you do get an even number, then our non-trivial square root is, so that we get x to the x to the r equal to 1. Then our non-trivial square root of 1, we hope, is x to the r over 2. We might be unlucky and get minus 1, in which case, again, we try again with another x. And on average, as I haven't justified, I might discuss that a little bit more on Friday. You expect to get an x pretty soon with this process. Of course, all that is conditional on actually being able to find the order of x mod n in the multiplicative group mod n. Then we stopped thinking about that for a little bit, and last lecture I concentrated on the quantum Fourier transform. So what we proved last time was, again without going right into the absolute details, but what I hope I convinced you of, is that if you've got a state that takes that form, then we can very easily send it to this Fourier transform. So this notation, this x, is standing for the integer x, but we can also think of it as a sequence of bits according to its binary representation, and the same with r. And so there's a clever way of writing the Fourier transform as a product, or tensor product of some small 2x2 matrix all the way from 4x4 matrix. Anyway, that gives you that transformation. And the other thing that we talked about was that if you've got a Fourier transform and you happen to have a function that looks like sum e to the 2 pi I alpha x 1 over square root of n, then what the Fourier transform will give you is a function that's extremely concentrated on values of r such that r over n is approximately equal to alpha. So what that tells us is that if we ever were lucky enough to have a function that looked like this, and to be in a position where we were very keen to have an approximation to alpha, then all we would do is take the Fourier transform, and that would put this thing into a state that would look like some, let's just give it some names, sort of mu r, and mu is the Fourier transform of this function, and mu r would be very, very small, except if r was very close, or except if r over n was very close to alpha. And then, in order to find out our approximation to alpha, we would just take a measurement in computational basis with high probability that would give us an r that was such that r over n was close to alpha. So that's the tool that we've got at our disposal. So the main thing I want to do now is to say, if you've got an x and you're trying to find an order, we can actually build something. This x is not the same as this x, but we can build something that looks a little bit like this, and alpha will tell us more or less what the order of x is in the multiplicative group. So because of that, we'll then just be able to say, well, now let's take a quantum Fourier transform, it takes no time at all, and we're done. But in order to show you how to do that, I'm first of all going to do it by a method that's blatantly circular and therefore sort of completely can't work. and then explain why the circularity actually doesn't matter at all. So the circular thing is to say, well, let's suppose that we could prepare before I say that, I think I'll first of all define a map. So given x, I'm going to define a unitary operator that depends on x. That will motivate what I was about to say. So we take our n. Actually, last time I had a convention that n equaled 2 to the n. I hereby change that convention for this lecture, because it's going to be convenient to have, well, you'll see what it is. So n is some large integer, and 2 to the n will be the smallest power of 2 that's bigger than n. So for this lecture, 2 to the n minus 1 is less than n, less than or equal to 2 to the n. So little n just is the number of digits I'm going to need in order to represent the interest in n minus 1. So my possible states will be everything from 0 up to 2 to the n minus 1. I ought to draw attention to an unfortunate ambiguity that arises here, and it actually will arise. Is 0 referring to some bit, or is it referring to the number 0? So here it's referring to the number 0. So if I expanded this, it would be 0, 0, 0, 0, 0, 0, 0, n times. But I think we can live with that. It's fairly clear, I think, in the context when I'm talking about the integer. This is binary representation of what I'm talking about, just a single qubit. So I'm going to find a unitary operator, which will be very simple. It'll just be permuting things, and it goes like this: that U maps A to AX if 0 less than or equal to A less than N. So that's AX mod N, but I think I won't keep saying mod N. All the multiplications I'm going to do will be mod N. That's the world we're living in. And so I'm only really interested in the states that correspond to the integers from 0 to n minus 1, but I've got to define U everywhere, so let's just define it. Just not to do anything if A is bigger than N. But I don't really care what this definition is for, it's something that's easy to do. So now I've got a bijection from the set 0 to 2 to the n minus 1 to itself. So this is a unitary operator. In fact, it's a permutation matrix. A very simple one. And also, it's something that's easy to compute. Classically, if I give you an A, it's easy to multiply it by x mod n. And here's another point where I'm not going to go into too much detail, but I talked about reversible computation and indicated that any classical computation you can do using reversible computation and getting some extra rubbish. So for this lecture, there's actually one subtlety that I need to discuss at some point, and I won't discuss it today. For this lecture, let's just take it as read that, because you don't go too far wrong if you do this, that I can just sort of insert easy classical computations anywhere I want into what I'm doing in the quantum world. And there are ways of achieving that with a quantum computer. So, of course, all the classical operators I do will have to take polynomial time, otherwise it would be ridiculous. But as long as that's clearly the case, then we'll be okay. So this is a nice, easy thing to achieve on a quantum computer. I'll just take whatever this is and multiply it by x mod n. Except if it was bigger than or equal to n, which I don't do anything before. Right. Now let's suppose we could, this is what I was about to say before, we could create a state which I'll call US, and that's exactly the notation that Nielsen and Schwang use in their book, which is that R is the order of x, it's 1 over the square root of R times the sum j equals 0 to R minus 1 of e to the minus 2 pi I js over R times j. said that this was a rather outrageous thing to do, to suggest. And what's the circularity? Well, we're trying to find the order of x, which is r. So how do we create something that involves r? I'll come to that later on. At the moment, let's just imagine that we knew how to do that, and ignore the point that if we knew how to do that, we'd already have r. We're going to find r, not by saying, oh, there's r, but a slightly more complicated way that will be more useful to us when we take into account that we can't actually create US just like that. Now, what's the point? What's the significance of US? I think I've just got that. That's not exactly what I wanted to say. Sorry, I meant to say x to the j. Sorry, it makes much more sense. So x to the j is going to be this. Right, so let's apply u to this thing. And also because I'm getting sick of writing e to the minus 2 pi I, I'll use the notation which is common in analytic number theory, which is that e of alpha equals e to the 2 pi I alpha. So this is e of minus js over r. The one thing to remember if you want to get used to this notation follows obviously from definition. E of alpha plus beta equals e of alpha, e of beta. If you just think it's a function that has that property, then it sort of helps to be. That's not meant to be a deep statement. It's just meant to be, if you bear that in mind and have not seen this notation before, it just helps to think about it. Rather than keeping on having to translate into e to 2 pi I alpha, then do the calculation, then translate back to the e notation. Just bear that fact in mind. It means you can think about it directly. Okay, so what is it? Maybe you can all see what the significance of US is in relation to capital U. It's sort of one obvious significance that it might have, and I'll check that it does have that. Well, it's that it's an eigenvector of U. So let's apply U. This is pretty trivial, but I'll write it out anyway. So we get e to the minus 2 pi I. Having introduced the notation, I forgot to use it. Well, it's going to come in more than just this once. But still, e minus js over r x to the j plus 1. And if I change my variables from j plus 1 to j, or, tell you what, I'll change this j to a j plus 1. So then I've got j plus 1 going with j plus 1. But to compensate for that, I've now multiplied by e of minus s over r, so I have to say that equals s over r US. So US is an eigenvector of capital U with eigenvalue e of s over r equals e to the 2 pi I s over r. So now let's suppose, this is not such a supposition, I'll maybe convince you of this. What we're trying to do, we're trying to produce let's make it 1 over 2 to the n. I'd like to produce something like that. So what I really want to do is, well, here's what I'll do. I'll start with the state times US. The next step is that I'm going to apply Hadamard gates to each of these noughts. Now, if you remember from last time, what happens if you apply Hadamard gates to each of the qubits of naught? You end up with just a sum over all epsilon, up to the normalizing factor. Because the first row of the Walsh matrix is 1 over root 2n all the way along. So applying Hadamard gates to every single qubit here, this goes into the following state. Sum, but I'm not going to reference, I'll write it as in terms of integers, so it'll be sum j equals 0 to 2 to the n minus 1 j times us with normalized capacity. So that bit was an easy thing to do quantum mechanically. I just applied the Hadamard gate to every single qubit of the initial noughts. So I've got the quantum computer, assuming I could get this US in the first place, I've got the quantum computer into this state. And now, what I want to do is I want to say, well, the next operation will be, I look at what this J is, or look at what I've got here, and do U that number of times to US. So I'll just write what the next stage would be, and then I'll try and convince you that this also could be done on a quantum computer. Well, it's kind of encouraging that U to the J did a unitary operation over here. The way to think about it is, we know how to do U, and we know how to do U squared, and we know how to do U to the fourth, and we know how to do U to the eighth, and so on, because U is just taking your number and multiplying by x, U squared is multiplying by x squared, U to the fourth multiplying by x to the fourth, and all those are reasonably easy. Whereas multiplying by x to the 2 to the k is all right, because repeated squaring is all right. So what you then do is you say, well, let's look at the bits of j, j1 up to jn, and each time you get a 1, so if I see a j1 there, then I'll apply the operator u 2 to the n minus 1, and if I saw a naught there, I wouldn't have done that, and then say the next one was a naught, and I wouldn't do the next one, and the next one would be 1 again, and I would apply u to the 2 to the n minus 3, and so on. Of course, all this is in superposition. That's a sort of slightly strange thing to think about. So to think about it, you just say, let's imagine we're in the classical world. Here's the classical computation I'll do. I'll look at the bits of this and multiply by appropriate x to the 2 to the whatevers. And then I just take a linear combination of what I was doing, and I get a sort of superposition. If you don't stop to think too hard about what might be actually going on physically, it's very simple. You just, in a way, it's very similar to what you do in a probabilistic computation. Sort of with a certain probability, you'll do various things, but now we're just taking an L2 sum instead of an L1 sum. So, strictly speaking, the language, if I happened to have J here, this is what I would do, is not completely accurate. We need some kind of quantum mechanical language for if-then. So it is a sort of L2 if-then instead of an L1 if-then. But, again, I'm not telling you something that's totally false with this description of what can be done. You can just do some classical stuff in superposition. Doesn't mean you're in superposition, but it's an allowable operation. Now, once we've done that, so this is the kind of thing I may try to talk about slightly more next time. So we're just breaking it up into very, very simple unitary maps. But I hope it's sort of believable. So if we can do that, then this equals 1 over root 2 to the n, sum j equals 0 to 2 to the n minus 1, and then u to the j of us is just because us is an eigenvector with eigenvalue es over r, we get e js over r us. And let's just think of that as 1 over root 2 to the n sum j equals 0 to the n minus 1 e js over r j to a massive factor around us. This is another thing. It looks as though I haven't done very much, but there's something sort of interesting going on there, which is the phase EJS over R sort of naturally attached itself to the US. But I thought I'd actually rather leave the US on its own and bring the phase over here. And that is an allowed thing to do, because it's just a tensor product of J with J, which contains a whole lot of bits, and US, which contains some other bits. Actually, US is itself a superposition of other things. That's an allowable thing to do, but it's sort of crucial to the notion of what you can compute, because now I'm just going to say, forget this bit over here, and I'm going to think about this part. Well, what happens to this part, what I want to do now is say, well, I've got exactly the sort of functions I was interested in. This is of the form, this is, well, let's just remind you what this really is. That's e to the 2 pi I j s over r. So that's e to the 2 pi I alpha j, where alpha equals s over r. Now using, if I then apply a quantum Fourier transform to this, I will get myself into a state, as I said before, that will output some, well, I get myself into a state which, when I measure it, it'll give me the bits of some number which is within, say, 10 over n of s over r. So I can find some beta, let's say, such that beta minus s over r is less than or equal to 10 over n. So just to repeat why that's the case, if I apply the Fourier transform to this, I will get some function that's extremely concentrated and near some t over n, or on values of t over n such that t over n is very close to s over r, within, say, 10 over n of s over r. That was the calculation I did at the beginning of the last lecture. So we've got ourselves into the position where we've managed to find some real number that's a very good approximation to the rational number s over r. And if we choose capital N appropriately, sorry, if we choose, maybe I've said something not quite right here. I'm going to put a square there, or maybe even a sort of constant times n squared. Because the accuracy of this computation here, so that depends on the size of the group that you're doing the Fourier transform in. So I should put 10 over 2 to the n there. Everything else that I wrote, actually, miraculously, seems to be correct. I do want to stop at n there, and when it's greater than or equal to n, I don't want to do that. So the point is that by choosing the number of bits here, the little n, I can get this approximation to be as accurate as I want, and it'll turn out that the accuracy that I will want is not too huge. But we now have the following problem. Well, I've got two problems. One is, how did I create that state in the first place? Perhaps I'll say that one next, because otherwise it just looks so ridiculous to keep going with this calculation. So, how do I solve the problem that getting US in the first place was not a feasible thing to expect? Well, we live in a world of superpositions. And why did I want S over R? Why not go for 1 over R? Because that would just tell us what R is straight away. Well, it's because I can't get S over R. So what I've done is, and similarly, I can't get 1 over R. So instead I've just gone for a general S, because if you can then observe that if you just sum over all S, you get a very, very simple state which you can produce. So let me just give you that calculation. What is 1 over the square root of R, sum S equals 0 to R minus 1, US? Well, it's 1 over R, because I've got two 1 over root R's floating around. Let's, we all know that I'm going to have to reverse the order of summations at some point. So let's do it try and do it in advance. So I'll first sum over j. And then I've got my x to the j, sorry, that's my US's. And now I'll sum over s. And I'll write in my e minus 2, minus js over r. And I'll bring the 1 over r over here, so it's slightly nicer. And what is 1 over r sum s equals to r minus 1 e to the minus js over r? It's delta j naught. If j equals naught, then I'm summing 1 r times and dividing by r. I've said this kind of thing quite a few times now. And if j is not naught, then you're summing over some roots of unity that are spread around the thing and you get 0. So this is just x to the naught, which is 1. And this 1 is not a cubic 1, it's the 1 that looks like this. Nevertheless, that's not such a challenging state to prepare. Let's put the last qubit as a 1 and all the other ones as zeros. So I can at least get the sort of L2 average, so to speak, of the US's, which are all orthogonal to each other. So everything I just said, I can't do for an individual US, but I can do it for a superposition of all the US's. And then later on I'll do a measurement, and so what I'll be working out is not a very, very good approximation to S over R, but I'll be getting a very, very good approximation to some random S over R with S between 0 and R minus 1. Now sometimes that's going to be a little bit disappointing. If S was 0, then I get a very good approximation to 0, and I wouldn't be particularly happy about that. Similarly, actually, if I'm trying to work out R from a random approximation to S over R, supposing I worked out exactly what S over R was, how would I know whether I've got 2/3 or 10/15ths, so to speak? Supposing I've got 2/3, it wouldn't actually tell me that the order of x was 3. It could be anything that's a multiple of 3. So now again, I'm trying to decide precisely what order to say it in. So there are two things I've got to talk about. One is that problem, what to do. Supposing I manage to get S over R exactly, that still doesn't tell me what R is. Let's sort out that problem first, and then let's talk about actually how you do get S over R. Because in fact all we've got is a real approximation to it. So the first problem is actually not such a bad problem. I'm trying to say there are 3 ways around it. I'm going to give the sort of least elegant way around it, which is, supposing you get a random S over R, and you want to know what R is. If S has a common factor with R, you have a problem, because when you put it in its lowest term, it doesn't tell you what R is. But if S and R are co-prime, then you won't have that problem. How can you be sure that S and R are co-prime? Well, you would be absolutely sure if S were prime. So one thing you could do is you just keep on choosing random S's with probability 1 over log n, which is polynomial in the number of bits. You do actually hit a prime. And you can use randomized tests for primality. I mean, we're very much in the randomized world, to test whether you have got a prime. So one very inelegant way would be you just keep going until your S is a prime, using randomized tests for primality. And when S is a prime, you're absolutely guaranteed that the denominator of your fraction must be R. But there are cleverer ways, like choosing a number of different S's and looking at the lowest common multiple of their denominators and arguing that after a while you must have taken account of all the possible common factors and that sort of thing. Probably you can't have all that many numbers that are co-prime. Maybe you could just choose random ones and take the largest denominator that you get after a while, and with high probability that would be R. All sorts of ways one can imagine thinking about it. So I told you one that's horrible, it works, so let's just assume that we're all right. So if we do enough runs of this algorithm, we'll be able to, and if we can always work out S over R from the approximation to it, then we'll be okay. So let's focus instead on the question, how do you work out S over R from a close approximation? So let's just think of a problem. Supposing I've got a number like supposing some real number comes out like that, and you have the information that real number is actually rather close to a fraction with a small denominator. So small in the case that we'll be interested in will mean less than or equal to capital N. And we'll be, supposing you're told you've got a real number that's really quite a lot closer to some fraction with the form S over R, with R less than N, than you have any right to expect. So it's sort of within 1 over N squared or something like that. That's a carefully chosen number, in fact. So how do you decide what the fraction is? Well, in this case, people may have already spotted. Does anyone spot? Somehow, if you're at all sort of nerdy in the right sort of way, then when you see something like 5714, huge bells ring, because you're familiar with the decimal expansion of 1 over 7 as 1.42857. But supposing we didn't know that, how would we work out that this was actually very close to 2 and whatever it is, number of sevenths? Probably 4 sevenths. Well, you could argue as follows. Supposing, first of all, this number, well, secretly, this number is close to 2 and 4 sevenths. With a number like that, there's something you can do to it, which is work out its continued fraction expansion. And when you do so, it doesn't take very many steps in the sizes of the denominator. It takes the number of steps to work out, to turn a fraction into a continued fraction is logarithmic in the size of the denominator. Let's say the numerator is roughly comparable in size to the denominator. So you might think, well, if you apply the continued fraction, if you work out the continued fraction expansion of this real number, then it should be very close to the continued fraction of this random number. Sorry.
So I'm confused by something. When we measure this beta, we measure it in the computational basis state. So beta represents an integer, not a general real number. So shouldn't we get an integer that is close to S over R and not a real number?
Wait a minute. Just. I think what the Fourier transform gives you, when we had this function that was of the form 1 over root 2 to the n sum e to 2 pi I alpha, let's use a similar notation we got here, j. It gave us, what it actually gave us was 2 to the n times alpha. So we're interested in what alpha is, so we just take that thing and divide it by 2 to the n.
So we take a measurement of something, divide it by 2 to the n.
So we'll take the measurement, it'll just give us the binary expansion of alpha. So just see if I can say anything more to make that completely clear. Yes. Okay, so here's the point. It was an integer, but I was talking about, if you talk about it in integer terms, then f hat of r equals sum e to the 1 over root capital N e to the 2 pi I r x over n. And it's this over n, which in our case is 2 to the little n, that is what. So we've got two integers here, but we mustn't forget the division by n in the Fourier transform. So what we outputted last time was the integer that was concentrated around r, but that integer divided by capital N. So if we now write something else that's e to 2 pi I alpha j, then that alpha is a sort of alpha over n times an n or something like that. Anyway, so it definitely does give us not an integer, which would be, it either gives us an integer or an integer which we then divide by 2 to the n. So when you apply the continued fraction algorithm to this, well, let's just quickly do it. We get 2 plus 4 sevenths equals 2 plus 1 over 7 fourths, which is 1 plus 3 fourths equals 2 plus 1 over 1 plus 1 over 4 thirds, which is 1 plus 1 over 3. And then it stops. So what do you do here? Well, you just apply the continued fraction algorithm, and you'll get, because it's close to this number, something that goes 2 plus 1 over 1 plus 1 over 1 plus 1 over, then you'll suddenly get something that's extremely close to an integer. And because you've got something extremely close to an integer, you'll recognize that your original number was close to a fraction. And then you can say what that fraction is by simply taking this number that's very close to an integer, or 2.99995 or something, and turning it into 3 and then working out what the continued fraction is, and you'll get the fraction that approximates your decimal here. So, how much time have I got? Perhaps I can say that a little bit more precisely. Supposing you've fixed your little n to be a lot bigger than n squared, if I've got a number alpha, and then I know that I can get it so that alpha minus r over s is less than or equal to 10 over 2 to the n, which is less than or equal to, say, 1 over 10 capital N squared, if I choose that C appropriately. That's going to determine uniquely what r over s is. Because if I take two fractions, r over s and r dashed over s dashed, because I know that s, so that's s over r. I know that this r is less than or equal to n. And if I take two fractions that have denominators less than or equal to n and they're distinct, so s dashed over r dashed minus s over r, what's the difference between them? Well, it's s dashed r minus r dashed s, which is at least 1, divided by r dashed r. At least 1 over n squared, and that's where the 1 over n squared comes in. No two distinct fractions with denominators less than or equal to n can be closer than 1 over n squared. So I know that if I find an alpha that's a lot closer than 1 over n squared to s over r, that determines what s over r is. And how do I actually find the s over r that's close to alpha? By working out the continued fraction expansion of alpha. And the convergence of the continued fraction, it is a well-known fact about continued fractions, are guaranteed to give you, for every n, the fraction with the denominator less than or equal to n that is closest to your real number. So, and it's an efficient process because effectively you're doing Euclid's algorithm in disguise when you're working out the continued fraction expansion. And Euclid's algorithm is a nice, quick, efficient process. So, I have actually just finished the proof of Shor's algorithm as it works, at least in a slightly informal way. But perhaps it's worth just recapping once more. So, we reduce it to the problem of finding the orders of numbers. We then observe that the state 1 is a superposition of eigenvectors of the map that takes A to AX. And I should say A to AX. So we just sort of think in superposition, and we say, well, if we took one of these eigenvectors and applied this process here, then we'll get ourselves a function of j, or the amplitudes associated with each j will just go round and round and round in a nice regular way. And because they go round and round in a nice regular way in powers of e to the s over r, they're exactly the sort of function that you really can understand by taking the Fourier transform. So very, very regular trigonometric type functions, because you're expanding in terms of a trigonometric basis, produce extremely concentrated functions once you take the Fourier transform. And extremely concentrated functions are the ones that you can actually measure and get useful results out of. It's not quite the case because we have to take the Fourier transform mod 2 to the n for some little n, that we can get it concentrated as an exact delta function. And another way of thinking about that is what I talked about when I was doing that bit, that this function that goes round and round doesn't go round an integer number of times between 0 and 2 to the n minus 1. So it's not quite totally perfectly set up to be calculated by the Fourier transform. If it had gone round an exact number of times, then we did do the Fourier transform and you just get a function that was 1, and we tell you exactly what s over r was, and 0 everywhere else. Unfortunately, we don't quite have that, but we approximately have that as long as we make our 2 to the n big enough. So we do all that, and if I take the whole thing as a superposition, what I'll actually get is not a function that's heavily concentrated in one place, but I'll get a superposition of functions that are concentrated on all the different values of s over r as s goes from 0 to r minus 1. At this stage, I do a measurement, and I'll get a random one of these things. So I'll approximate some random s over r. Then I use continued fractions to tell me exactly what the fraction s over r was, and then I can do my ugly thing of saying, was s prime? Oops, no, it's composite, so let's run the whole thing many times until we do get a prime. That says what r is, that says what x to the r is, and then we're going to say after all that effort, x to the r over 2 went and equaled minus 1. So let's start again. But all this is in the sort of theoretical world. We don't really mind in this particular game starting again, as long as we only have to start again polynomially many times, which is typically the case here. So next time I'm going to try to explain a little bit more of the details, like exactly how to understand the quantum Fourier transform as a composition of very simple unitary maps. I've sort of indicated what I've indicated so far is plausible that it can be done. I'm just going to tie up little loose ends. I hope to be able to convince you that accidentally getting a trivial square root of 1 doesn't happen all that often, and that sort of thing, or doesn't happen often enough to be a problem. And I'll also mention something about embedding classical computations into quantum computations using reversible computation. There's something called uncomputation that turns out to be. If you'd seen what I've done here, you won't have noticed that there's a slight problem about one aspect of it. So, very roughly speaking, when you do the quantum computations, and then you do a bit of classical stuff, there were those garbage bits that I talked about, and you might have left them over here, and that might have just sort of messed up the superposition that you've got here. So, strictly speaking, what I've said here is slightly problematic. So I'll just tell you about a trick called uncomputation that, so to speak, takes the garbage and tidies it up. And that turns out to be a surprisingly straightforward thing to do. So it's going to be bits and bobs. If this is the main point of everything, I'm going to finish now, I think, rather than try and fill the next 5 minutes. So the main point of Shor's algorithm is now being done. But there are a few details, and they're quite interesting. And one other thing I'll do next time is talk about, which is perhaps slightly more interesting than dotting I's and crossing T's, just talking about one or two other problems that can be done using Shor's algorithm, or using these sorts of ideas. In particular, the discrete logarithm problem. So we found orders is pretty plausible. That seems very closely related to the problem. I give you a generator, and I give you an x of the multiplicative group mod n. What power of the generator is x? That's a discrete log problem. And that can also be done with the help of this, these sorts of ideas. I'll just say precisely how that works. I think it may well be the case that the next lecture will also not go the full distance, but I've got a few things to say.